Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review everything you need to know for the upcoming test. So there's two topics that will be on the test, and I'll do this video in two sections. The first is index laws, and then we'll go on to exponential growth and decay. So I'm sure that you've seen these index laws before. What we'll do is we'll go through each law one by one with a couple of examples. So the first law is when you multiply the bases, so here A is the base and B and C are the powers, you multiply the bases, keep the same base, and add the powers. So very simple examples. If you have like x to the power 3 times x to the power 5, keep the same base, and add the powers. So if you have numbers involved, you just do numbers and letters separately. So if you had 4y squared times 7y to the power of 3, 4 times 7, 28, keep the same base, and add the powers. How easy is that? So the second index law is similar, but instead of timesing the bases, we're going to divide them. So when you divide the bases, you keep the same base and subtract the powers. So, for example, if you had like a to the power of 10 divided by a, you keep the same base and subtract the powers. Now, note that a and a to the power 1 are the same thing, so this would just be a to the power of 9. So, as a slightly harder example, if you had something like 12x to the power of 5 over, let's say, 20x to the power of 4, do the numbers separately again. So 12 by 20 simplifies to 3 over 5. X to the power of 5 divide x to the power of 4. Keep the same base, subtract the powers, you're just left with x. So the next rule is if you have two powers. So if you have a power that is raised to another power, once again, you keep the same base and you multiply the powers. BC, of course, means B times C. So if you have something like x to the power of 4 to the power of 7, you keep the same base and you multiply the powers. 4 times 7 is 28. So next up, we have the zero index. So if A is not equal to 0, then A to the power of 0 is equal to 1. In other words, anything not 0 to the power of 0 is equal to 1. So, for example, 2 to the power of 0 is 1, x to the power of 0 is 1, as long as x does not equal 0. So if you have something like 7x to the power of 0, you're raising everything in the brackets to the power of 0. That is 1, as long as x is not equal to 0. But if you had something like 8x to the power of 0, once again, x not equal to 0, this time only the x is raised to the power of 0, so it's 8 times 1, which is 8. The next law is that the power of the products is the product of the powers. So if you have a product, a times b to a power, you just raise the first thing in the product to the power times the second thing in the product also to that power. So if you have something like 2x to the power of 5, people always mess this up. They forget that you have to raise the 2 to the power of 5 as well. So 2 to the power of 5 is 32, and then you raise x to the power of 5 as well. So if I combine this with the third index law, if I have something like 3y squared to the power of 6, you go 3 to the power of 6, which is 729. Now, y squared to the power of 6, keep the same base, and multiply the powers. That's the third index law there. Okay, so that's what the answer would be. So second last index law, if I have a fraction, so a over b, and I raise it to a power, it's very logical. You just simply raise the top of the fraction to that power, and raise the bottom of the fraction to that power. So for example, let's say I had x over y to the power of 3. All you do is raise x to the power of 3 and y to the power of 3. So as a slightly harder example, let's combine it with the third index law as well. So if I had something like a squared over b to the power of 4, and I want to raise it to the power of 5. So you raise a squared to the power of 5. So using the third index law, keep the same base, multiply the power. So it's a to the power of 10 on top, and then we raise the bottom to that power. So keep the same base, multiply the powers. A to the power of 10 over b to the power of 20. Now, just a quick note. The powers are 10 and 20 in this fraction here. You can't simplify this fraction. It doesn't matter that 10 and 20 have common factors because they're part of the power. That cannot be simplified any further. All right, the final index law involves negative indices. So if you have, say, a to the power of negative b, it doesn't become a negative number. What you do is you just put everything with a negative power on the bottom of a fraction and write it with a positive power. So for example, if I had 7 to the power of negative 2, it's just 1 over 7 squared, or 1 over 49. If I have something like x to the power of minus 5, same thing, it's just going to be 1 over x to the power of 5. Now, if I have many things in the expression that I want to simplify, anything with a positive power goes on top, anything with a negative power goes on the bottom. So if I had something like 8p to the power of minus 1, q squared, r to the power of minus 3. So the things with a positive power go on top, so that's 8 and q squared. And the things with a negative power, so these two here, they go on the bottom, but I write them now with a positive power. So once again, this fraction here cannot be simplified, and I'm done. So they are the index laws you need to know. There's 7 there, most of which you encountered before this year. I'm just going to go through a few examples now where we have to use multiple index laws. So let's simplify this expression here. I know it's complicated, but we're just going to use the index laws one by one as required to make this much, much simpler. So firstly, you know from what we did with algebraic fractions, when you're dividing by a fraction, you flip it and make it a times. So everything else is going to stay the same for now. So the first fraction stays like this, and I flip the second fraction and I make it into a times like this. Okay, so now we want to do the brackets first. So the laws that we're going to need, we need the power of a product and also power to a power. So we raise x squared to the power of 3, keep the same base, multiply the powers. Then we raise y to the power of 3 also, and then we can leave the others as they are for now. So what we do now is use the first 2 index laws, the basic ones of multiplying and dividing. So if I multiply the tops together, like top by top, I will just get 8x to the power of 6 times x to the power of 5 is x to the power of 11, and the y cubed just leave by itself. And then on the bottom, I have 4. The x stays by itself. Now y to the power of 7 times y is y to the power of 8. So now I go 8 divided by 4 is 2. X to the power of 11 divided by x is x to the power of 10. Now y cubed divided y8. Don't do it any differently. Keep the same base and subtract the powers. Okay, so we did 3 minus 8 because the 3 is on top. Now, oftentimes you'll get questions saying, write your answer with only positive powers. So in this case, everything with a positive power goes on top and negative powers go to the bottom, but write them with a positive power. So the final answer is 2x to the power of 10 divided by y to the power of 5. Okay, we're going to look at one more example of index laws before we go into exponential growth and decay. So we're actually going to simplify this expression on your screen and write it with just positive powers. So this actually requires quite a few index laws. So firstly, the fractional index law. So what we do is we raise the top of the fraction to the power, and we raise the bottom of the fraction to that power. Now remember, power to a power. So if I'm doing this, I keep the same base, I multiply the powers together. On the bottom, keep the same base, multiply the powers together. Now I want to write this with just positive powers, okay? So the a to the power of negative 8 is on top, so I'm just going to move it to the bottom. So I'm going to put a 1 in its place, and I've got this. But the problem is the b to the power of negative 12 still has a negative power. So we can sort of reverse what we were doing before. So I said, if you have like a to the power of -5, you move it to the bottom of the fraction, right, with a positive power. Well, it turns out if something has a negative power and it's on the bottom of a fraction, you just move it to the top and write with a positive power. Okay? So basically, when you're raising something to a negative power, you switch it between the bottom and the top. If it was on the bottom, you move it to the top. Top, you move it to the bottom and write it with a positive power. So what am I blabbering on about? Well, of course, that means I'm going to move the b to the power of 12 to the top. Okay? So I used a lot of index laws here, and hopefully that helps you understand them better, but there's a quick way to do it. If you have a fraction, x over y, say to a negative power z, you can just flip the fraction and raise it to a positive power. So in this case, I could have done it simpler. I could have flipped the fraction and made it a positive power, and I would get the exact same answer. B to the power of 12 over a to the power of 8. So as an exercise to really understand the index laws, you might want to see if you can prove some of them. And please feel free to ask me help if you want this. But now I'm going to go on to exponential growth and decay. Please pause and copy this down if you need. So we now turn our attention to exponential growth and decay. So this is where a quantity is increasing by the same % each period, like each year or whatever, or it's decreasing by the same % each year. So the best known example of exponential growth is compound interest, which you would have learned about. So we're going to go through that. Now, we're also going to contrast this with simple interest. So this is just hopefully so you'll understand compound interest better. Simple interest is not exponential growth. Again, I just want to contrast them, okay? So let's look at an example. So to compare and contrast simple interest and compound interest, we're going to look at the example of investing $2,000 at 5% per annum, which means per year, for 12 years. So simple interest, as the name suggests, is very simple. Simple interest, I can just calculate 5% of 2,000. So that's really easy. You probably don't even need a calculator because you know that 10% is 200, so 5% is 100. So under simple interest, it's going to go up by $100 a year. So at the end of year 1, we're going to have $2,100 in our account. And at the end of the second year using simple interest, it's going to go up by another $100, and we're going to have $2,200, and the end of year 3 is going to be $2,300, and so on. I'm sure you get the idea. Okay, so you can easily figure out that after 12 years, so at the end of the 12th year, it's going to have gone up by $1,200. So I'm going to have $3,200 all up. That's easy. That's not exponential growth. But let's look at what happens with compound interest. In compound interest, for the first year, it will go up by 5%. So remember, increasing by 5% is the same as finding 105% of the number, which is the same as timesing by 1.05. This is timesing by 1.05, the same as increasing by 5%. So at the end of the first year, I will have $2,100. But at the end of the second year, instead of finding 5% of 2,000 and adding it, I find 5% of 2,100 and add it. In other words, I increase my new amount by 5%. It's going to go up by 105. So now, after the second year, I'm going to have 2,205. So at the end of the third year, I don't increase by 100 again, as I did in simple interest. I take my new account here and increase by 5%, which is the same as timesing by 1.05. So I'd have 23, 15, 25, okay? So what is happening here is each time in simple interest, it's going up by $100, okay? That's pretty simple. Every year goes up by the same amount. But what happens with compound interest is it increases at an increasing rate. That's what exponential growth is. First year it increased by 100, then it increased by 105, Then it increased by $110.25, increasing at an increasing rate. Now, if I want to find how much I'd have after 12 years, I don't want to go through this process. This was just to help you know what's going on. What you see is I'm taking my original amount and I'm timesing by 1.05 each time. So after 12 years, I would have this amount of money. You put that in your calculator, no one's expected to do it in their head, you have about $3,591.71, just rounding to 2 decimal places because it's money, okay? So this is a much faster way to do it. What I want you to understand, it's exponential growth because the amount by which the investment is increasing is going up each year. Each year it's going up by more and more. So the formula we use for compound interest is A equals P, so that was our 2000 principal, what we started with, times 1 plus R over 100. So R is the rate, 5%. So in our example, 1 plus 5 over 100 is 1.05. That's because if you want to increase by R%, it's the same as finding 100 plus R%. You want to increase by 10%, same as finding 110% of the amount, etc. And what we need to do is raise that to the power of n, because we're multiplying by this n times, where n is the number of recalculations. Okay, so that is our formula for compound interest, and it turns out we'll be able to use it for other examples of exponential growth. So this example, compound interest, we were calculating the interest at the end of each year. So what we say in this case is that the interest is compounded annually, meaning we recalculate the interest at the end of each year. Now we're going to look at examples where we don't calculate the interest at the end of each year. So please pause and copy down this slide if you need. So we return to our example on the previous slide. If I invest $2,000 at 5% per annum for 12 years, and in blue is the formula we had on the previous slide. So we figured out that the answer was $3,591.71. That's to 2 decimal places. That's when we were calculating the interest at the end of each year. So we got to the end of year 1, recalculate the interest. End of year 2, recalculate the interest. But let's look at what happens when we don't do it annually. So as it says in yellow, we're going to look at what happens when the interest is compounded monthly. So rather than recalculate how much money is in the account at the end of each year, we're going to do it at the end of each month. So fortunately, we don't have to go through some long process. We can essentially use the same formula. So P, the principal, will be the same, however much you compound it. But what we're going to do is we're going to say this R, which is the rate, that's going to be the rate per period. It's going to be, in other words, the rate per the compound period. So if we're talking about compounding monthly, we're going to change R to the rate per month. Now, N is still the number of compounds, but if we compound monthly for 12 years, suddenly there's not going to be 12 compounds as there were in the previous example. The number of compounds would be 12 a month for 12 years, which is 144. So what does this all mean? Well, in this case, R is 5% per annum. So what it's actually going to be per month is 5 over 12% per month. So 5 over 12 is 0.416 recurring. So it's 0.416% every month. That is the number we need to substitute in the formula. And as I said, N will now be 12 compounds a year for 12 years, which is 144. So if I want to invest $2,000 at 5% per annum for 12 years, and interest is compounded monthly, the amount I will have at the end of the 12 years is now principal, which is the same, times 1 plus rate over 100 to the power of n. So it's the same formula, but the R and N values have changed. So if we put that on our calculator, we get approximately $3,639.70. So you can see it's a little more than what we got when we compounded annually. So if you change the frequency of compound, it does change the amount of money you have. The more frequent the compound, the more money you have. So if I were to do this again and calculate it, if interest was compounded weekly, I'd get even more money than $36.39. If I was going to do compounded daily, I'd get more money still. So the more frequent the compounds, the more money you have. And of course, monthly is more frequently than annually. Weekly is more frequently than monthly, and so on. So you use the same formula in each case, it's just the values of R and N will change. So I'm not going to show you just for time's sake, but if I want to do compounded weekly, now R would be 5 over 52% per week, and N would be 12 times 52. 52 a year for 12 years, which is what, 624, okay? I want to point out that when we're using this formula for compound interest, it calculates the amount in the account, not the interest. If I wanted to figure out how much interest I'd actually earned, you just take the amount. So if it was compounded monthly, this would be the amount that I have, and then you subtract what you started with, which was obviously 2,000. So I would have earned an extra $1639.70 in interest in this case, okay? So that's all well and good for compound interest. Let's look at other examples of exponential growth and decay. So let's look at this question here. We start with a single cell, divides into 2 every 2 hours. How many cells would there be after 24 hours? So what's happening is you start with 1 cell, then after 2 hours you have 2 cells, then 2 hours later, 4 hours, those 2 have divided in 2, so you have 4 cells, and then after 6 hours, those 4 divide in 2 and you have 8 cells, and so on and so forth. So this is an example of exponential growth because, once again, the number of cells is increasing the increasing rate. First 2 hours, it increased by 1, then by 2, then by 4, then it'll increase by 8 cells in the next 2 hours. So because it's exponential growth, increasing at an increasing rate, we can use our formula, the same one for compound interest. But the difference is just the meaning of the variables, right? So P meant principal for compound interest. Here it's just going to mean the initial amount, what you start with. R is still going to be the rate of increase. It's just not an interest rate anymore. So the rate of increase, and N is the number of increases, similar to the number of compounds. We can use this formula here. So we know that we start with 1 cell, and we know that if it increases every 2 hours, it'll increase 12 times in 24 hours. But what is the rate? So all we need to know for this is that if you double something, that is the same as increasing by 100%. So you know, like if a company puts a 100% markup on something, it doubles the price, for example. So what would be the answer to this question? So the amount after 24 hours is equal to how many you started with, which is 1. So that's P times 1 plus, I said R was 100. 100 over 100 to the power of, and there are 12 increases in 24 hours because it's every 2 hours. You put this on your calculator, you just get the number 4,096. So after 24 hours, there'd be 4,096 cells. Once again, this is exponential growth because the quantity we have is increasing at an increasing rate. Now we're going to look at an example of exponential decay. Let's look at this example here. Population of a town, 300,000, decreasing by 5% each year, and we'll figure out how many people will be in the town after 20 years. So this is an exponential decay question because the number is decreasing by the same percent each year. So at the end of the first year, we'd subtract 300,000 by 5%. So there'd be 285,000 people in the town. So at the end of the second year, we don't decrease 300,000 now, we decrease 285,000 by 5%. And we end up with the number 270,750. So what's happened is that from the first year to the end of the first year, we lost 15,000 people, but then in the next one, we only lost 14,250. So in exponential decay questions, the amount is decreasing at a decreasing rate. In other words, the number of people that leave the town each year decreases each year. It's not as though 15,000 are leaving the town every year. That's just in the first year. So we can use a very similar formula. So the formula for exponential growth was A equals P1 plus R over 100 to the power of N. Right? So remember, when we're not talking about compound interest, P is the initial amount, R the rate of increase, and N the number of increases. So how can we change this formula when we're decreasing? So you know that if I want to say increase by 5%, I told you that's the same as timesing by 1.05, because increasing by 5% is the same as finding 105% of the amount. Now, it turns out that if you want to decrease by 5%, you're finding 95% of the amount. That makes sense. If your favorite shirt's on sale, 5% discount, you're only paying 95% of the original price. So finding 95% is the same as timesing by 0.95. But that's the answer I'd get if I got 1 minus 5 over 100. So what I'm saying is, when you are doing decreases, the only thing you change about the formula is instead of a plus in the brackets, it becomes a minus. So this is the formula for exponential decay when we're decreasing. We're now ready to solve this question. It will just be initial amount times 1 minus rate of decrease over 100. And once again, to the power of the number of decreases this time. So it'll decrease 20 times in 20 years. And if you put that on your calculator, to the nearest whole number, you get 107,546. So that's about how many people will be in the town after 20 years. So you can see that that is roughly about 35% of the original amount, because it's decreasing at a decreasing rate. All right, there's just one more thing I want to go through, and that's where we're going to find the value of P. Let's look at this example here. Bought a car 10 years ago, value decreased by 12% each year, now worth $4,000, and we're going to calculate its original value. I don't want anyone thinking, oh, 10 times 12 is 120%, so the value must have decreased by 120%. No. This is exponential decay because the value is going down by the same percent each year, which means the actual amount by which the car is valued each year is decreasing at a decreasing rate. So if it loses like 5,000 in the first year, it's going to lose less than that in the second year. So how would we actually solve it? Well, let's go to our formula, A equals P1. Now, because we're talking about decreasing value, we're going to do a minus 1R over 100 to the power of N. So what we do, as we do in so many problems in maths, we substitute everything we do know and rearrange for what we don't know. So A is the amount that it is worth now, just like in compound interest. A is how much I have now at the end of the time. So A is in fact $4,000. The car didn't start at $4,000, it ended up at $4,000. So that's why I'm substituting A for $4,000. We know what R is because it's decreasing by 12% each time. So I'm going to replace R with 12. So it says that it's decreased by this amount each year for 10 years. So once a year, each year for 10 years, of course, that means N is 10. So the thing we're trying to find out is P, the original value. So all we need to do is rearrange this equation. So how do I actually do that? Well, what I'm going to do is I'm going to put this into my calculator because it's just a number. So this is just 0.88 to the power of 10. So if I put 0.88 to the power of 10, I'm leaving the 4000 and P as it is. I get the number about 0.2785. So remember, this is a times there. If I want to get P by itself, I undo timesing by 0.2785 by dividing by this. So P will just be 4000 divided by 0.2785. And the answer I get, this time I'm just going to round to the nearest dollar, but it wouldn't matter if I rounded to cents. I get about 14,363. So that's the original value of the car. If I bought it for 14,363 and it decreased by 12% each year for 10 years, after 10 years, it'd be worth 4,000. Okay, so this is just solving an equation as you've done a million times. All right, once again, sorry for the long video. Thank you so much for watching. Best of luck studying for your test, but you're a superstar. You will ace it. This is the luckiest maths teacher in the world. Have a great day.